Hello, my name is Carson Meyer, and I am presenting aluminum oxynitride, or more commonly referred to as transparent aluminum. So, aluminum oxynitride, usually referred to as ALON, was originally manufactured by the Cermet Corporation in 2010. ALON is a transparent aluminum ceramic. So instead of glass, which is amorphous, ALON is a ceramic, which means it has a crystalline structure. ALON is optically transparent up to 80% on 2 mm slices in the spectrum bands of low energy UV, visible, and mid to high energy IR spectrums. It is the hardest transparent polycrystalline ceramic available commercially. Alon has a cubic spinel crystal structure. It is composed of alternating tetrahedrons and octahedrons with aluminum centered in the middle. The linear formula is AlNX mixed with Al2O3 1 minus X, where X equaling 5/14 is the most stable, clear, and structurally useful allotrope, also commonly referred to as gamma alon. So when manufacturing this for military purposes, they mix 5 parts of aluminum nitride and 9 parts of aluminum oxide together. The manufacturing process occurs in 2 different stages. First, the aluminum nitride and aluminum oxide powders are mixed together in the ratio that I just mentioned. They are then subjected to extreme pressures in a mold to form an opaque brick in the necessary shape, whether it be a tube, a dome, or a sheet. Finally, the brick mixture is sintered to around 2000 degrees Celsius to give Alon its signature optical and physical properties. A common challenge with the sintering process is finding a crucible that can achieve the proper temperature without leaching any stray ions into the mixture. Also, the powders must be incredibly pure before they are used, as any other impurities can reduce the visibility. Also, sometimes magnesium oxide is added in to increase the overall density, or better to say, decrease the porosity. Many different mixes are used to create Alon, but the one that's used industrially and to make stuff for the military is that ratio of 5 to 9. So Alon was originally intended for military applications to make bulletproof windows, as it's much lighter, almost 4 times lighter than glass laminate, and much more durable than glass laminate. It also has superior resistance to oxidation and radiation, giving it a longer projected service time. Here is a snippet from a video. I couldn't get the video to play in this recording, but it is linked in the references. Cermet released a video where they demonstrated shooting a 50 caliber bullet at a sheet of Alon and a sheet of glass laminate, showing the physical superiority of Alon. It also succeeds in military applications because instead of shattering like glass does, when a chip is formed on the surface of Alon, it merely flakes off in its crystal boundary instead of forming a shatter that goes through the entirety of that layer. So in that case, you don't need to laminate layers of Alon together. If you wanted a better resisting to pierce layer, you would just make a thicker layer. I have some physical properties up at the top, which you could use to compare to other materials that have similar use cases. An alternate use proposal, which is something that I came up with, is using Alon as material for the reactor core of a 4th generation nuclear reactor. Some of these reactors are posing to use liquid fuels, liquid fluoride salts. A lot of them use beryllium as a moderator. And so these reactors need exceptional resistance to heat, exceptional resistance to not only gamma radiation but neutron radiation, and they also just need to be strong because these reactors, even in the pilot stage, are running many kilograms, if not tons, through the reactor at a time. And because Alon is made of relatively low molecular weight atoms, it has good reflectivity of neutrons, which allows breeder reactors to have a better neutron economy. It blocks radiation, gamma radiation, almost as good as concrete does, so it requires less shielding. Its melting point of 2100 C is far above the 600 to 700 degrees C that these reactors run at, and it is very, very corrosion resistant, which is a major issue posed for these reactors. So my idea was that it would make a great containment material for these reactors, and also it can be pressed into various shapes and then sintered, so the manufacturing process for the parts for these reactors could be made modular and could be done at a specific site, and then these parts be shipped off to the reactor site instead of them being manufactured on site. Here are my sources. Thank you for listening.